Okay, so I'm going to start working on building models for the Bird Song Classifier project. And as we already discussed before, we already did all the EDA and everything and the data cleaning. And I also defined the class methods, which I will be using to extract the features for the training and the validation sets. So if you haven't already, be sure to watch the video on the class methods because the class methods are quite large. And I'm not going to go over them here right now. So it would be a good idea if you're going to use the class methods to get an idea of what the class methods are doing. So to extract the features from the training and the validation sets, it takes quite a while. So I already went ahead and extracted them in this notebook. So I first imported the libraries. We have the drive access, the standard libraries. We have the audio features. That's the librosa and the audio for the libraries for the audio features. And we have some pre-processing, which is label encoder, which we will use to encode the classes, the labels, the three species to 0, 1, and 2. And then we have the min-max scaler, which is going to be used for normalizing the features. And I am actually going to move this because I want this one-hot encoding to be in the pre-processing step. So we're also going to use this one-hot encoder to encode the continents to a one-hot representation. And then for the modeling, we're using TensorFlow. So actually for here, the TensorFlow is used to do the average pooling. So I'm actually going to move the TensorFlow to the pre-processing step as well. And so for modeling, we're really just using the scikit-learn random forest classifier. And to review the output, I'm going to use the classification report from scikit-learn as well. And in case there are any visualization, I'm going to use matplotlib and seaborn. Okay, so here I included the self-defined class methods for feature extraction. As a reminder, we have the framed and the extraction classes. The framed class is going to frame the audios to the 5 seconds window with the 2.5 second overlap. And the extraction class is going to extract the specified features based on the list that's being passed into the as parameters. So I first load the CSV file, which is the train val CSV file, where we specified the set, whether the row belongs to the training or the validation set. And I just wanted to take a look at how many rows. So we have 1,000 rows for both training and validation. And then I use the framed class to extract the framed object, which is going to contain the train data frame and the validation data frame. So to run this class on 1,000 rows, it took around 5 minutes. And here I can take a look at the framed train data frame, which includes a new column of framed. This is a list of the 5-second clips from each row. You know, when the duration is more than 5 seconds, or when the duration is more than 7.5 seconds, it's going to extract more than one clip from each audio. And same for the validation set. Here we can see here the set is validation, and we have the framed column as well. And then we specify the features list that we will be using to pass into the extraction class instantiation in order to extract the features. So here I only have MFCC, chroma, RMS, spectral centroid, mel spectrogram, and continent. So I didn't include type because if the model is really for an average user, then for an average user to upload a audio file in order to get the bird species, the average user wouldn't know whether the bird is making a call or a song type. So here I don't want to use the type as one of the features. And then for rating, we really don't want the rating to be a distinguishing feature because just because one species has more audios with a good or bad rating shouldn't be a distinguishing feature for the model to learn whether that audio is belongs to a particular bird or not. But the rating could be very useful when we start to build neural networks where we can give audios with better quality rating more weights during training. So I will discuss this once we get there. But for now, we're just doing the random forest, so we don't really need the type and the rating. Okay, so then I instantiate the extraction class by passing in the train and validation data frame and the features list, and I want to normalize and average pool. Again, as a reminder, if you try to extract all these numeric features without average pooling, the kernel will crash. So this instantiation of the feature extraction process took around 15 minutes. This is actually faster than expected. Sometimes this takes almost up to a half hour or 40 minutes. And as you can see here, if you click on the right-hand side here, you can see the system RAM. I'm already using half of the RAM. Once we start to build neural networks, this is going to take up even more RAM if we don't do the average pooling. Okay, and similar to what I already showed in the class methods video, here is where we can extract the train labels from the features and also the train features. This is the train features is in the form of a dictionary. And we have around 8,000 training samples. And here's where we extract the validation labels and the validation features. The features, again, are in the form of a dictionary. We have around 4,000 validation samples. Okay, so now that the features and labels have been extracted using the class methods, I'm going to move on to start building the model. The first thing I want to do is I want to encode the classes. So the classes are the labels or the species. So in this case, we have 3 species. And here you can see in our val y and x and train y, the array, the NumPy array for the species is actually still the species name, but I want this to become 0, 1, and 2. So I'm going to use the scikit-learn label encoder to encode the labels to 0, 1, and 2. Okay, so to encode the labels, I'm going to first instantiate a label encoder. Again, this process you can you can find the documentation of how to do this on the scikit-learn website. So I'm going to fit the training y. You should always use the training to fit, whether being label encoder or min-max scalar, it should be fit using the training data only. And then I'm going to transform the training data using this label encoder. Okay, and the same thing I'm gonna do for the validation. Okay, and one other, so now this is already pretty what I would want for the train y and val y. One other thing I want to do is I want to actually take a look to see, you know, which other number correspond to which of the class, because this label encoder is doing this automatically. So I am going to create a classes variable, which is going to tell me which one is which. I'm going to use the label encoder inverse transform by fitting in the 0, 1, and 2. And this is going to tell me, you know, which of the 3 species is 0 and 1 and 2. And then I can take a look at the classes. Okay. So here we can see Barswa is 0, Comsen is 1, and Earwag 1 is 2. And if we take a look at the train y, we can see it has been successfully transformed to 0, 1, and 2. And similarly for val y, it has successfully been transformed to 0, 1, and 2. So here I am going to actually print out, display some information. Display, this is going to be, should be learn. So I want to make sure that I have around 8,000 still training samples. And I want to take a look at the first 5 training Y. So this is like a list indexing. Okay. And then I'm going to do the same for the validation. Okay. All right, so here we can see that we still have the around 8,000 samples, and the training and validation is has been successfully encoded. I am actually going to change this to 10. Okay, so you can see earlier when we had only 5, right? It seemed like everything was encoded to 2 for the training, but it's just by coincidence that well, not by coincidence, because the first 5, 1, 2, 3, 4, 5, 6, the first 6 are probably from the first row of the example, right? Remember, so here when we have, for example, a duration of 17 seconds, it's going to frame, our framed class is going to frame this based on 5-second clips with 2.5-second overlap. So it's gonna create a number of different, framed audios, each with 5-second length, right? So we're going to actually need to shuffle. The next step is that we're going to need to shuffle this so that we don't have like the features and the labels of the same class all stacked next to each other. Because if we do it like this and just directly feed into the model, it could make the model become kind of biased in the sense that it could quickly learn the features from the class 2 because it only sees the class 2. And then when we start to give it class 0 or class 1 later on, the model could have a hard time picking up the features from these other classes. Okay, so I am going to shuffle the data now, and I'm actually going to define a function where, because I need to shuffle for both training and test. And I'm going to pass in the input label and the input features as parameters. And how do I want to do this? I want to first find out how many classes there are. So here we already know we have 3, but just in case, we just want to use a function for this. So input label. Okay, and then I want to set a random seed. Just so that this could be reproduced. Okay, and I want to indices. I want to find out what the indices is for the permutation. Okay, so what this is doing is I'm using this numpy random function. That permutation is going to basically shuffle the input len, and then it's gonna give me the indices, which I will use the indices to shuffle the label and the features. So since the features is in a form of a dictionary, I am going to use a dictionary comprehension. Array features. Input indices. Okay, let's just make sure. For our input indices and for key in input features and the input labels. I am also going to use I'm going to use a list comprehension because the input labels is in the form of a list. I'm actually gonna cast this to a NumPy array. Input label I. Okay, so if you're unfamiliar with the list and the dictionary comprehensions, so it's basically I can write this in the form of a for loop. So I can say for I in input indices and then colon, and then on the next row I can put input label I, right? And then I'll just put, so this section is the same as if I created a new list. And then for I in input indices, new list dot append input label I. So this is gonna be similar to this list. The list comprehension can be written down in the form of a for loop as well. And the same thing for the dictionary. It's just for the dictionary, I have an inner this inner list, which is cast to NumPy array first. And then I have the key value pairs where the key is for the key in the input features. So you can think of this as a nested for loop. So first I have for key in input features, and then I have for I in input indices. Okay, so after I do this, I'm going to return the input labels and the input features. I actually just want to reuse the label and feature. Okay. I think this is right. I'm going to try using this for to shuffle the training dataset. Okay. So it looks like it may have worked. I'm also gonna use it to shuffle the validation dataset as well. Okay, and well, since this is done, I am going to display the shuffled chain Y and the chain features and the shuffled val Y and val features. I'm just gonna copy the same thing as I did up here for the validation. It's the same information. I just want to confirm that things have been shuffled. Okay, so the same thing for the chain. I'm going to just copy the same code as above. Okay. Let's see. So this looks like, why does it not look like it was shuffled? Maybe we just have too many, we just have too many examples. Let's just take a look. Let's see. Okay, so I think what happened was I copied this whole chunk here where it's actually doing the train y equal to features dot train y. It's not giving me the shuffled train y. So I am going to just rerun this again. Let's just rerun from here so that our train y is the original train y. Okay, and that's right. And then we want to shuffle the data. All right, so this is much better. As you can see here, the data has been successfully shuffled. Originally, we had like 6 of the class 2 all stacked together, but now we have the class 2 and 0 and 1 all mixed. And same thing here, I'm going to just loop through the train features and take a look. Okay, and then I also want to shuffle the validation. And again, I just want to look at the validation. Let's look at the first 15. And the validation has also been successfully shuffled. And I also want to look at the validation features. Yeah, so this is what I was expecting. And now I'm going to do the one-hot encode continents. So the reason why I need to do one-hot encode continents instead of just using the label encoder to encode the continents is, so here we have, I think, 6 continents. If we use the label encoder to encode the continents to be 0, 1, and 2, and 3, etc., that is going to make the model think that the items with the higher numbers are more important. So I don't want that. I just want the model to treat them as all equal. So what one-hot encode is going to do is, if I have 6 different continents, it's going to create 6 different columns. And in the first row, if my continent is Europe, it's going to show 1 in the Europe column and 0 for all the other columns, and so on and so forth. So for the one-hot encode continent, I am actually also going to use the scikit-learn library, and they already have a one-hot encoder method I could use here. So I am going to use the one-hot encoder, and first step is I'm going to define encoder. I'm going to set the sparse output equal to false. This detail can be found in the documentation, so I'm not going to go over the details here. I'm just going to write out what I want to achieve. Features, continent. So I first want to reshape this, reshape the train and the vowel continents. So in case you're not sure, you can always look at the shape. Yeah, so you can see the shape here is a A236, and what it's gonna do is shape. Yeah, so it's gonna make this 2-dimensional instead of 1-dimensional. Earlier we only have the A236 comma, and then the 1 is missing. So now I'm just adding the 1 here so that it becomes 2D. Because that is the shape the method is expecting. So I am going to do continents equal to encoder dot fit transform. So here it's okay to do fit transform because there's really no difference between the train and the validation. So I'm gonna fit transform the train continents for the train continents, and I misspell continents. And then I'm going to do the same thing for the validation. Okay, and now I want to take a look. add the train continents. Let's just take a look at the first 5 rows. And the same thing for the validation. Right, so for example, you can see here, the first 5 rows, the first row is, we created is effectively 5, 1, 2, 3, 4, 5. So we have 5 continents, 5 columns here. And each of the continents is only, it's like an on and off switch, right? So like here, on this column, it's on all the other columns are off. And then for this one, this column is on and all the other columns are off, and so on and so forth. Okay, so now I created the one hot and cold continent. I am actually going to start running the random forest models. So I want to first create a dictionary to store my results. Because I plan to run multiple models with different combinations of features. So the first one I want to run is to run it with all features. As a reminder here, we have, let's take a look. We have the MFCC, chroma, RMS, spectral centroid, Mel spectrogram, and continent as our features. So I'm just going to concatenate using the NumPy concatenate to concatenate all the features into one big feature called training features. I forgot. I'm actually going to copy this just so that I know which ones I need to add here. Chroma on RMS. Spectral centroid. I always misspell this one, so I'm just going to copy paste it here. And now spectrogram and continent. Actually, continent. Remember, we made them one hot, so I'm just gonna add the train continent, which is a one hot representation of the continent instead of the original continent. Okay, and I want to concatenate this on axes equal to 1. Okay, let's take a look. Okay, let's take a look at the shape actually. All right, so remember earlier we had each of the features, for example, MFCC, we had a shape of 8200 by 20, and chroma is 8200 by 12, and etc. So here I just concatenated them. You can think of the 8236 as the number of rows and the 59 as the number of columns. So we have MFCC, we have 20 columns for MFCC, and then 12 columns for chroma, and then 1 column for RMS, 1 column for spectral centroid, 20 columns for Mel spectrogram, and then 5 columns for training continents. So that all adds up to 59 columns. Okay, so I'm gonna do the same thing for the validation. So make sure that all of these are updated to using val features dictionary. If not, this concatenation is actually going to fail because the number of rows don't match. Okay, so this should work. And it did it. Let's see. Val features, val features, val features. Let's just make sure. Index 0 has 2 dimensions and array at index 5 has 0 dimensions. Index 5. 0, 1, 2, 3, 5. Oh, that's because I accidentally put this as val features. It should be val contents. Okay. There we go. So this was concatenated successfully, and let's just take a look at the shape again. We should expect the same number of columns. Validation features. Okay, yeah. So we should expect the same number of columns. Again, 20 MFCC, 12 chroma, etc. added up together is going to be 59 columns. And for validation, we have 4,000 rows. Okay. So now we have the data ready. I am actually going to delete this and add a little subtitle here. Features. And then we're going to start running fit the model. Fit the model with training data. Okay. So the random forest is actually quite straightforward. We can just directly use the scikit-learn ensemble. Here we already imported the random forest classifier. So I am going to just use the random forest classifier. And I want to use an estimators equal to 50. And criterion, I'm going to use the entropy. Okay, so these are hyperparameters that could be tuned. I'm just using this to start with to see how the model would perform. And I am going to fit using the training data. This is going to take a minute to run. Okay, so now the random forest has been fitted with my training data. I'm actually going to print the training accuracy. There's a in the random forest, I can call random forest.score to get the training accurate to get the score. You can see here on the training data, our score is actually 1, which means everything was 100% classified into one of the 3 species. Okay, so I'm going to just clean this up a bit. And I'm actually going to add this score into our results dictionary. And I'm going to do the same for the validation. Okay. As we can see here, the training accuracy is 1, but the validation accuracy is only 67%. This is actually not bad considering we have 8,000 training examples. Our baseline, if we were to think of this as if we were to randomly guess, then we should expect our validation accuracy to be around 33% because we have 3 species, three classes. And with no class imbalance issue in the training set, we should expect if we were to randomly guess, then we should get the correct class 33% at the time. But here our validation accuracy is actually 67%, which is actually not bad. And I'm going to evaluate the results by putting it into a confusion matrix. Okay. So first thing I want to do is predict the chain Y hat. This is the same as a fit since I'm just doing the training data. And I mostly wanted to use get the chain Y hat result is so that I can look at the classification report. So in case you're wondering, we can actually take a look at the chain Y result. And we can actually look at how that compares to chain Y. You can see here, just look at the first three and the last three, they're exactly the same, okay? So then I'm going to use the classification report. Let's see, print. Going to add a new line, and then I'm going to print the actual classification report by calling the classification report function, which is again part of the scikit-learn library. I'm going to pass in the true Y and the predicted Y. And the target names is gonna be classes as what we put earlier. Otherwise, it's just gonna show 0, 1, and 2. Where's the target classes? Here, remember we use the label encoder inverse transform to reverse transform 0, 1, and 2 to classes, so that here we can visualize using the actual class name instead of just 0, 1, and 2. Okay. Yeah, so here on the classification report, you can see we have the precision, recall, F1 score, and the total accuracy, overall accuracy. And we have 3 species here. And I'm gonna actually do the same for the validation set. All right, so on the validation set, we can see that our overall accuracy is 67%, which is the same as what we saw earlier. And if we want, we can again take a look, for example, how the actual label and the predicted label differ. So I'm gonna put got Y here. Okay, so just looking at the first 3 example and the last 3 example, we can see in the first 3 example, we have the first one, which the true label is 2, but the model predicted to be 0. And the second one, the true label is 0, the model predicted to be 2. But all the other ones seem to be correct. So just taking a quick scan at this, the 67% accuracy seems reasonable. The model is not doing 100% well, but it's also not doing too badly. And the next thing I'm gonna do is I'm going to run the generate the confusion matrix. So the confusion matrix is going to help us visualize how well the model did for each of the species. Even though we can already see here, for example, if we look at the F1 score for Barswa is 0.72, clearly the model is doing better with Barswa than Consent and EWAG1. But if we put into a confusion matrix, we can better visualize this. Okay, so I'm going to first calculate the confusion matrix. I'm going to use the TensorFlow math confusion matrix to calculate this. The documentation, you can look at it yourself. Okay, so this is gonna just give me the train confusion matrix. You can take a look. So here, this is the confusion matrix, and I'm just going to plot it using Seaborn so that it's a little bit easier to visualize using a heat map. And I want and notate equal to true. And I want to present, I don't want to use the scientific notation. Sometimes it does that. And I want to use the blues color map. And I want to change the tick labels. Again, the classes, the same thing as we did earlier. Otherwise, it's gonna just show 0, 1, and 2, and it's kind of hard to see. Put 0, 1, 2 to the different species. I don't want the color bar. Okay, and to make this better, I'm also going to add the axis labels. Okay, so the x-axis is gonna show the predicted label and the y is gonna be the true label. And best practice, following the best practice, I'm also gonna give it a title. And I'm gonna do plot show. Yeah, so now we have the confusion matrix for the training data set. We can see that the x-axis is the predicted label and the y-axis is the true label. For example, we have 2,700 samples for bar swap, and the model was able to predict 100% correct, and the same for each of the other 2 species. And we can do the same thing for the validation as well. I'm just going to copy this and change this to use validation data. Change this. All right, so now we have the validation confusion matrix. You can see here that there are more colors than the training confusion matrix. So for example, if we look at bar swap, our total true label is 1100 plus 241 plus 352. This row added together is gonna equal to 2758, which is the total number of bar swap as true labels. And of the 2700 true bar swaps, the model predicted 1100 to be bar swaps, 241 to be COMSAN, and 352 to be EWAG1. And similarly, we can interpret the other 2 in similar manners. For example, COMSAN is going to be this row added together. It will be the total true label for COMSAN. And the model predicted 757 to be correct, and the other are incorrectly predicted to be other species. Okay, so this is the random forest model using all the features. And I'm just going to create the same thing by using different combinations of features. For example, MFCC, chroma, RMS, spectral centroid, null spectrogram, and continents. I'm going to pause the recording while I update this to include all the other features, and I will be back to present the final results. All right, so I have added many, quite a few models, the random forest models, using different combinations of features, as you can see here. And then I created a data frame which summarizes the training and validation accuracy for each of the features. So as we can see here, this is the summarization. I created, let's see, I think 16 total different models with the different combinations of features. MFCC appears to be the most predictive single feature comparing to, for example, chroma or MEL spectrogram. And RMS and spectral centroid have the least predictive power as expected because they're only a one-dimensional representation of the audio features. And in terms of using MFCC as the main audio feature, with the combination of MFCC, chroma, and continents, we were able to achieve the validation accuracy of 70%, with the MFCC and the continents closely followed at 69%. So I wouldn't really say chroma added much, value into here, but just looking at here, I think something that we can conclude is that MFCC is certainly has more predictive power than MEL spectrogram, just from the way that we have processed the data. And MFCC and continents, the two features as a combination are more predictable, have more predictable power than any other combinations alone. So going forward, I will be using this kind of structure to run multiple different models using different combinations of features on the ensemble, which is the random forest and XGBoost, as well as the vector machine and logistic regression. So the thinking is, if these are some of the more traditional algorithms, and if I use these algorithms to run the different features, then I can try to gauge which features have more predictive power than the others. And when I move on to the more complicated neural network, I can just use the features that have the most predictive power. So that's it for this video, and I will see you next time for XGBoost, support vector machine, and logistic regression. Thank you.